Okay, welcome to Chapter 30. In Chapter 31, we're only doing a little bit. This Chapter 30 packet we'll do in 2 videos because this one packet is like a book. And so we're going to take a look at Chapter 30. Chapter 30 now is about putting magnetism and magnetic components into circuits and seeing how circuits work with magnetism and that sort of thing. So induced current is the current produced in a loop by changing the magnetic field. That's different from regular current where we set up a potential difference, an electric field, basically inside the wires. Induced EMF is work done per unit charge in producing a current, right? And so again, we can think of this as EMF is electromotive force. We're not setting up a potential difference. Instead, what we're doing is we're doing work on the charges by changing the magnetic field. Induction, the process of producing current and the process of producing EMF, so induced, right? Faraday's law of induction. The idea is that the EMF in a loop, when the number of magnetic field lines that passes through the loop changes. Now, if we think of a loop and the number of field lines going through that loop, it's like, wait a minute, that looks like flux, right? And so if the flux is changing, that induces current. So that's the idea. A changing magnetic flux induces current. And you think changing current or changing flux, that's going to be a derivative, right? If we think in terms of calculus. And then Lenz's law tells us that the induced current is produced to oppose the change in magnetic field. And so we know that a current produces its own magnetic field. And so if the magnetic field is getting smaller in one direction, the current that's produces a magnetic field that is increasing in the opposite direction, right, from the one that's getting smaller. So there are three discoveries here that we go through. One, current appears only if there is relative motion between the loop and the magnet. So if we have a loop set up next to a galvanometer, which measures very small current, and you pass the magnet into and out of the loop, the only time where you get current being produced is when the magnet is moving. Okay, the faster the motion, the greater that current that's produced. And then the opposite motion of the magnet produces opposite direction of current. So if we move the magnet in one direction and we get current in one direction, if we move it in the other direction, then the current goes in the other direction. So the direction that the magnetic field is changing makes a difference for the direction of the current. Okay. The other thing that we can do is we can set up a magnetic field instead of having an actual magnet, a bar magnet, is you could have a magnetic field produced by current in a loop. So you could have 2 loops together. You turn on the current, that current produces a magnetic field, and when that magnetic field is changing, when the current is starting to go through, then you get a changing flux. The changing flux produces a current in the other wire that's hooked up to the galvanometer. The only time you're going to get current going through that wire with the galvanometer is when you're turning the other circuit either on or off, because that's the only time you're having a changing magnetic field. All right. So let's see. Qualitative generalities. Induced current appears only when there's a relative motion in the loop of wire in the externally created field. So current's created even though there are no batteries or capacitors. Don't need batteries, don't need capacitors. But it will get interesting if we throw some capacitors in there to see what happens. And current stops flowing when the relative motion between the loop and the field stops. All right. Faster motion, more current. The direction of the induced current in the loop depends on the direction of the magnetic field and whether the field is increasing or decreasing. Induced EMF is the work done per unit charge in order to produce induced current. The process of inducing current and EMF is called induction, like we said before. And changing current conditions in one coil can induce current in a nearby coil or loop. And so, Chapter 28, we have a current loop and a magnetic field gives us torque. And then Chapter 30 tells us that if we have a magnetic field and a torque, that produces a current. Because we're going to have, basically what we mean here is that if I have a current loop and I'm turning the loop, then what I'm doing is I'm effectively changing the flux, right? Because I'm changing, remember, flux is B dot A, and so that includes the angle, right, cosine theta. And if I'm changing the angle between the area vector and the magnetic field, then I have a changing flux. Okay, and so magnetic flux, like we said before, is integral B dot dA, or BA cosine theta. This is measured in Weber, and there are three factors that can change flux, right? So changing flux, that would be the change in the field, the change in the area, right? So that means if I take a loop and I make the loop smaller, I'm changing the flux. Or changing theta, right? So again, the loop is turning or something like that. I'm changing the angle. That'll affect the flux and therefore produce a current. Okay, and so the law, and this is really basic, it's really simple the way this is, that EMF, right, so now we see epsilon again, but the epsilon here is EMF, not the permeability constant, 4 pi times 10 to the negative 7. So here EMF is equal to negative d phi b, so phi b the magnetic field, over the time, over dt. And so it's the negative of the change in the magnetic field with respect to time, or the change in the magnetic flux with respect to time. So negative d dt of the integral b dot dA, because integral b dot dA is our, what do you call that thing? The flux, and so it's negative d dt of BA cosine theta. And again, any BA or theta, if any of those things are changing with respect to time, then that tells us, we have a changing, or then we have an induced voltage, induced EMF. So the negative just tells us the direction, and most of the time we're going to ignore that and we're going to find the direction using the right-hand rule. But the negative is there for the formality if you are doing this mathematically. And the number of field lines doesn't matter. So in other words, if I have a huge magnetic field, but I only have a very, very small change in the magnetic field, that's going to produce a small EMF. So the size of the field doesn't matter. It's the change of the field that matters, or the change of the flux, I should say. Okay, so induction, and this is, so again, all of this is Faraday's law. So there are three factors: the magnitude of the magnetic field, the area of the coil, or the angle between them. And so here's what this means. If I have a magnetic field going this way, and I have a loop around, and this magnetic field starts to decrease, then I'm going to have a current produced in that loop that will go opposite the direction of the change. So this magnetic field is getting smaller, then the loop is going to produce a magnetic field in that direction. Okay, and then that would be, going like on the top of the loop away from me and towards you, and at the bottom of the loop towards me, because that would produce a magnetic field pointing that way. All right. So the thing to do, two things. Ask yourself the direction of the field, or what direction is the magnetic field, and then is it getting bigger or smaller? What current will produce a magnetic field opposite to that change that's happening? Right. So if I have a magnetic field that way and the magnetic field is getting bigger, then the loop will produce a current to oppose that, right? So then it would be going the other way. This current would be coming towards me on the top and towards you on the bottom, because that'll produce a magnetic field that goes that way. Okay. So induction scenario number 1. The magnetic field can change by changing the current in one coil. That'll affect the current in the other. Induction scenario 2. You are moving a bar magnet into and out of a loop or a coil, something like that. Or you can actually have, and we'll do this at some point, you can have one solenoid and another solenoid, and one going into and out of the other. So that's kind of like the other one, because the solenoid can pretty much be like a bar magnet. Induction scenario 3. You are changing the size of the coil, or the loop, right? You make the loop smaller, you're changing the flux. And so that induces a current. There, if you're making it smaller, then what's happening is you're reducing the flux. And so it's kind of like the magnetic field's getting smaller, and then it'll produce a current to oppose that, sort of almost like to try to increase the magnetic field in the same direction that it's going, of the magnetic field. Okay, or induction scenario 4, you have a loop that's rotating when there is a change in the flux, because you're changing that angle theta. So a lot of kind of qualitative stuff, it feels like here. All right, so know the direction of the external B field, and know how the B field is changing. And then you've got to use your right-hand rules to figure out, what direction the current's going to go to oppose the change in the field. Okay. So for example 1, the switch in coil 1 is closed. So if it's closed, then what direction will the induced current and EMF in coil 2 be as the switch is closing? All right. So a lot of picturing, a lot of right-hand rules here. So in coil 1, you can see that it closes, and there the current is going to be coming, let's see, so look at the positive side. It's going to be going this way, right? From where I'm reading it here, it's going this way. So it's going around, like up the back and down the front of that. All right, so that's going to produce a magnetic field going to the right. Okay, and then, so I have a magnetic field going to the right. That's an increasing magnetic field to the right. That means coil 2 is going to have an induced current producing a magnetic field going to the left, right? And so then that'll be up in the front and down in the back. And so that'll be going from D to C. In coil 2, at the bottom there, through the resistor, the induced current will be to the left, from D to C. Example 2. Okay, so again, now it's going, same thing as before, and there's no more current in the coil on the right, or the solenoid on the right, because it's not changing, right? It's just, briefly, that current was there. But now, in coil 1, it says, when we open the switch, so what's happening there? When we open the switch, so we had a magnetic field pointing to the right, but now that magnetic field is being taken away, because we're turning off the current in coil 1. All right, and so it's pointing that way. That means that coil 2 will want to produce a magnetic field going to the left. And so that means it'll be going up in the front and down in the back. Let's see if I got that right. Oh no, sorry. So coil 1 has a magnetic field to the right, but it's decreasing. So that means coil 2 will want to produce a magnetic field to the right, right? Because it's coil 1 to the right but decreasing, so coil 2 is going to oppose that, so it'll produce a magnetic field to the right. So that again will be up in the back and down in the front, so the current will be pointing to the right on the bottom, going from C to D. Okay, and then coil 1, so now example 3, there's current going through coil 1, and so that means there's a magnetic field to the right, and we move that one towards coil 2. What we're doing is we are increasing the magnetic field in the area of coil 2, and so coil 2 is going to produce a current to oppose that magnetic field to the left. And so that's going to produce a magnetic field where it's up in front, down in back, and so that means it'll be going down to D and over to C. So at the bottom, through that resistor, it'll be going to the left. Okay, in example 4, now we have a magnet, north and south. So this magnetic field points to the left, right? Goes from north to south. And so on the side there, where coil 2 is, it's going to be pointing towards the south end, right? Magnetic field lines point towards south, away from north. And so the magnetic field here on that side of the magnet. And so as we move this toward, it has a magnetic field pointing to the left, and it's getting, as the magnet is moving. So if the magnet is moving towards the coil, the magnet is moved toward coil 2, that means that we have a magnetic field to the left and it's increasing. That means that coil 2, the magnetic field near there, that'll produce a magnetic field to oppose it, so to the right. So that'll be up in the back, down in the front, and that means down to C and up from D, and so it's going to the right through that resistor in coil 2. That's example 4. Okay, and then example 5. Now again, this one is a little different because now the magnet's above, so those field lines are pointing from north, around, down, and back up to south. So here the magnetic field is pointing to the right. The magnetic field near this coil, is pointing to the right, and it's increasing because we're moving this magnet towards the coil. And so it's increasing in that direction. We're going to have an induced current to oppose that magnetic field, so it'll be that way. So that'll be up in front, down and back, right towards D, up from C, and so the the current in that will be going from D to C. All right. And so example 6, a square single turn coil, 0.2 meters on the side, is placed with its plane perpendicular to a constant magnetic field. An EMF of 18 millivolts is induced in the coil when the area of the coil is decreased at a rate of 0.1 meters squared per second. What is the magnitude of the magnetic field? So let's take a look at this mathematically. And we will go to the board for this one. Just cleaned it. It was really dirty. Okay, and so I have this equation written down that the EMF equals NB cosine theta dA dt. N is the number of turns, so that's 1. B is the magnetic field. Theta here is 1, or sorry, theta is 0, so this is 1. And so I'm just looking at B dA dt. B then is EMF over dA dt, right? The rate of change of the area. So this is 18 times 10 to the negative third volts. It's 18 millivolts over 0.1 meters squared per second, right? The unit's meter squared, seconds there. And so here I end up with 0.8 times 10 to the negative 2, or sorry, 18 times 10 to the negative 2, or this, so Webers. All right, and that's it. And we're going to skip example 7 for now because that's coming ahead, actually, that same problem. Right, so we're skipping number 7 for now. We'll come back to that in a little bit. These next slides are all review about Faraday's law of induction and the qualitative generalities. So next we're going to look at text sample problem 30.1. And the idea here is we've got a long solenoid, 220 turns per centimeter, and that carries a current of 1.5 amps in the diameter. And then at the center is a 130 turn closely packed coil of diameter 2.1 centimeters. And we want to know, so the current in the solenoid is reduced to 0 at a steady rate of 25 milliseconds over a steady rate of 25 milliseconds. We want to know the EMF induced in the coil and the direction of the induced current through C. Okay. So first of all, the magnetic field due to S, so the large solenoid, is uniform at the center, and it's directed towards the right. Okay, so towards the direction where it says axis over there on the right. And magnetic flux, so what's happening as we reduce the current, the magnetic flux is decreasing. Right, that magnetic field is decreasing, so EMF is induced in C, and the current in C is going to be directed up in the back and down in the front to increase to the right, right? Because the field is to the right and it's decreasing, so this is going to create something to oppose that, so to the right. And I think some more specifics are on the next slide, so you got to turn the page, and then you can see actually the calculations, right? So the EMF is negative N and then d phi dt, because phi is the thing that's changing here. So N is 130. We know that already. That's 130 turns of the coil. And then, so we've got BA cosine theta minus BA cosine theta. It's steady, so we don't have to take a derivative of a function. We just find the difference of the flux over the time difference right there. And the difference in the flux is, right, BA cosine theta. So the magnetic field is mu I n, where n is the number of turns per length. Pi r squared is the area, and the angle is 0. And so we can calculate what the magnetic field is with the flux, and then put flux divided by time, and figure out that it's 7.5 times 10 to the negative 2 volts of induced EMF. So now we're going to take a look at example 7, and let's go to the board for this one. All right, we have a toroidal coil. All right, so we have a toroidal coil, 4,000 turns of wire. All right, so based on the information, we want to express the magnetic flux of the first coil in terms of the current I. All right, so phi is BA cosine theta, but this is 1, okay, because theta is 0, and so the magnetic field is going to be mu naught I n over 2 pi r. All right, so we plug in, we can leave that. So now that's going to go in here, where B is mu naught, we'll make this a capital I because it's a constant current, times 400. Is that 400 or 4,000? This one's 4,000. It's being produced over 2 pi times 0.1. That's the radius. Okay, and then times A. So this is going to be pi r squared. So 0.75 times 10 to the negative 2. This whole thing is squared. So this ends up being 1.4 times 10 to the negative 6th. So we have this I in here, and so this is 1.4 times 10 to the negative 6th times I Webers. So this is what the current, this times the current will give us what the flux is. But we don't know the current. Okay. And these numbers, you know, if we're picturing this toroidal coil, it looks like this. And so from here to here, from the center outwards is 0.1 meters. From here to here is 0.75 centimeters. So now for the induced EMF, that's negative n d phi dt. So we're looking here at negative n, and now we're looking for the derivative of this. Right, it's actually a function. And so 1.4 times 10 to the negative 6th I over dt. Right, and now we have what this is, right? di dt, this is a constant. Di dt is the number that's given to us, the 25 amps per second. So this is 400 of 1.4 times 10 to the negative 6th times di dt, which is 25 amps per second, and we get 0.14 volts. Right. Okay. And then the textbook problem, example 13, or textbook problem 13, this is how you could solve it. All right, we're looking for finding the EMF due to a coil rotating at frequency f, and that looks like, you know, phi is AB cosine phi, and so what we end up with is AB, A times B, the magnetic field, times cosine omega t, because the thing is going to be turning, right? And so we substitute in now EMF is negative n d phi dt, and so we're taking the derivative of that whole thing with respect to time, and now the time is in the angle, in the cosine part of it. And so that ends up just becoming now n omega AB times B, the magnetic field, sine of omega t. And omega is 2 pi f, so we substitute in for omega 2 pi f. And so that's it. You just end up with this formula. All right, now let's take a look at example 8, and we can do this one on the board as well. All right, so what do we know about this? N is 200 turns. R is 0.1 meters. It's a coil. B is 0.8 Teslas. And so we're looking for this turns 90 degrees in 1.5 seconds. So it's 90 degrees in 1.5 seconds. And so that's, this is pi over 2, and this is 3 over 2 seconds. So this ends up being pi over 3 is actually our value for d phi, or d theta dt. Okay, and so the EMF, again, negative n d phi dt. Right, so this is going to be negative n b a cosine of theta dt. So b and a are staying constant, but the thing that's changing is theta here, right? So this is, sorry, this should be d ba cosine theta dt. Forgot about that. And then, so we're looking at n, negative n ba d cosine theta dt. Right, and so this ends up becoming negative n b a omega sine omega t, and that becomes positive. Okay, and now we can just plug our numbers in, because d theta dt is omega. That's what that is, right? And so when you plug in the numbers n 200, b is 0.8, a would be pi times 0.1 squared, and then omega would be pi over 3, and sine of, let me see that, yeah, sine of pi over 3, you plug in the number and you get 3.7 volts as your answer there. Right, oh, because you're plugging in 45 degrees as the angle there, so root 2 over 2. Okay, so that's it for example 8. Okay, example 9. So now we're going to be continuing this study. So what's happening here? Here actually the area, or the, okay, so we got a rectangular loop of copper located outside a uniform magnetic field. The loop is pulled to the right at a constant velocity v. Sketch the graphs for induced current and induced EMF. Identify which point is higher at a higher potential, C or D. Right. And so here's the idea. You've got, this is the area where there's the field, and you've got this loop that's being pulled through here. Right. And so this line here represents the front end of this thing. This is the, we'd say, the width. Right. And so when this reaches this point, right, when the front end of this reaches this point, up that time the flux through this loop is not changing. And so there is no induced EMF on this. Okay. Actually, let's look just in terms of current for now. Right, so there's no current being induced. But once it reaches this point, now we have a magnetic field inwards, and the flux is increasing into the page. And so as a result, this is going to produce current this way coming out of the page. Right? And so this is going to coming out of the page, so that's going to be counterclockwise, so a positive current, until this thing reaches a point where the whole front end is in, which would be somewhere in here, right? This is the width. And then now until the front end reaches this side, so that would be when the front end is over here. Again, this is going to be just 0 because there's no change in the flux. But once it's coming out, now the flux in is decreasing. So this is going to produce a current in, right, to make a magnetic field inwards. And so this is going to be curled around this way, and the current's going to be going clockwise until the front end, until the back end leaves. And so this is the width of this right here. Once the back end leaves, then it's out, and there is no more change in the current. Okay, and then, so this is for the current, and then for the EMF, we can repeat this same kind of thing down here. And so if there's no current, then there is no potential difference between these 2 points C and D, right? If C is over here and D is over here. And now if the current is going this way, then that means I have a higher potential at D than at C. Okay, and so that means wait, let's see. Oh no, it's going counterclockwise. At this point, it's going counterclockwise. So I have a higher potential at C than at D. And so that makes this positive based on the key. And then at 0, no potential difference. And then down here, since the current is going clockwise, I have a higher potential at D than at C. And so that's negative potential difference there. And then here, the potential difference. So really, this shouldn't be EMF. Let's call it V, potential difference between C and D. And then here at 0, because there's no current as a result. Okay, some of these next sample problems are based on 30.5. So we're just going to stop here, and we'll pick up with 30.5 in the next video.